Hello guys, in this video I'm going to talk about the bisection method to solve a nonlinear equation. This method is one of the simplest method in numerical analysis to solve and find the root of a nonlinear function. Before that, I'm going to talk a little bit about the intermediate value theorem. This theorem is the foundation and basis for the bisection method. Assume that we have a function fx which is continuous for the interval a over b. Here you see the function. The red curve is the function fx, and it is continuous and it is between a and b in this graph. So that's the first assumption. Also, the second assumption in this theorem is that fa is not equal to fb. So here you see fa and then here fb. So they are not equal. And the third assumption is that we can have a point K which is between FA and FB. So you see the point K here, and it is between FA and FB because the red curve function fx is continuous. So given these assumptions, there is a point such as psi between a and b, such that f psi equals k. So here you see that since the red curve is continuous, then we can have a point like psi on the x-axis, which is related to point k through fx. So we have these from the theorem. So then we can have our final conclusion. If FA times FB is negative, then the equation fx equals 0 has at least one root in the interval a and b. So you can see on the graph that since it's continuous, since FA is negative and FB is positive, then there is at least one intersection between the red curve and the x-axis at x null. So in other words, fx has a root at x null which intersects the x-axis, as we can see on the graph. So that's pretty much the intermediate value theorem, and based on this theorem we want to introduce the bisection method. Okay, in the bisection method we use a systematic approach of the intermediate value theorem I just introduced. We assume an interval a1 and b1 over which fx is continuous, and fa1 times fb1 is negative. In other words, it has a root in this interval. An iterative approach is used to converge to the root of our equation. I'm going to show you on this graph and also this table how this iterative approach works. We evaluate the function at the interval's midpoint and examine its sign. For example, here assume we are in iteration 1. So first column is I, standing for iteration. So we are on iteration 1. And we have A1 for the second column. For the third column, we have B1, as we see on the graph. Then the third column is the midpoint of the interval. which is defined as mi is equal to a1 plus bi over 2. It's a midpoint of the interval, ai plus bi, or a1 plus b1 over 2. So in the table we have a1 plus b1 over 2. The last column is for fmi. So let's look at the graph and find the midpoint of the interval a1 and b1. Okay, it's fair to say that the midpoint is around here, so we can assume it's m1, and then we have f of m1 here, which has a negative sign. So the last column is the sign of the fm1. Okay. We examine the sign of the midpoint, and we use the midpoint to replace whichever limit has the same sign. Here we see that f a1 is negative, f b1 is also is positive, and fm1 has the same sign as fa1, and we replace, for the next iteration, we replace a1 by m1. So as we can see in the table, for the next iteration, instead of using a1, we use m1, because a1 and m1 gave us the same signs for f, for the function. And the interval, the next one is the same, b1. So we have a new midpoint between m1 and b1. So over the graph, let's look at the new midpoint between m1 and b1, which is around here. It's we call it m2. It's fm2, which is positive. It has a positive sign. So in the table, it has a positive sign, the new midpoint. And okay, between m1 and b1, which one has the same sign as m2? Of course, it is b1, because as you see, both are positive. So for the next iteration, we keep m1, but instead of using b1, we use m2, which has the same sign as b1 from the previous iteration. And our new midpoint is m1 plus m2 divided by 2. On the graph, we can see it's very close to the root. It's m3, or it is fair to say that m3 is the root. So we are approaching to the root of the function, and after each iteration, the bounds containing the root decrease by a factor of 2. So that's pretty much the bisection method, which is very simple to understand. Now I'm going to give you a real example to show how the bisection method works, and I'm going to use a calculator to show and illustrate a graph. and the same table as we used here. Okay, let's look at this example where we have fx as x over 2 squared minus sine of x. The first thing that we have to do in the bisection method is choosing an interval, an appropriate interval where we have the root inside, at least one root. So one method to decide on the interval is graphing the function. So here I'm gonna use Desmos Calculator to draw the graph of the function fx. So let's look at it. Here we add expression and we can draw our function. So our function is x divided by 2 squared minus sine of x. So this is the graph of our function. As we can see, this curve intersects x-axis at 2 points. One is 0, which is obvious if we put 0 in the equation, we get 0. But we want to look at the other one, the other root. And we can see here it's somewhere between 1.5 and 2. Let's assume we decide on the interval of 1.8 and 2 based on this graph that we just drew. So getting back to our function, the interval of 1.8 and 2. So this is our A1 and this is our B1 as we explained before. So for the first iteration we have 1.8 and also we have 2. The midpoint of this interval is 1.9, which is the average of these two values. So we want to decide on the sign of this function at 1.9. So we get back to our calculator. So we have different values here by default by the calculator, but on the first row, we just enter 1.9. Okay. And that 1.9 is also shown here in the graph. And the value of fx is minus 0.0438. So it's the negative value. So the sign of m1 is negative. Let's get back to the table. So it is negative. And the sign of 1.8 is also negative, as we can see in the graph, and sign of 2 is positive. So it has the same sign as 1.8. So in the next iteration, we replace 1.8 with 1.9. 1.9 and then 2. And the midpoint of this new interval is 1.95. Let's decide on the sign of fx at this point. And we can see on the graph, or we just put simply 1.95, and it is positive. It's 0.0216. So you can see it's positive, so the sign is positive here. So for the next iteration, we replace 2 by 1.95 because 2 was also positive. F2 was positive. F of 1.95 is also positive, so we replace with the same signs. The midpoint of this new interval is 1.925, and the sign of the function at this point, at this midpoint, is, let's just write that, 5. It's negative 0.0115. So the sign here is negative. So we replace, for the next iteration, we replace it with iteration 4. We replace it with 1.925 with the first limit of the interval, and then 1.95, and the new interval, the new midpoint is the average of these two values, which is 1.9375. This is our new midpoint. Let's look at the sign of f x at this point. 1.9375. Okay, it is positive. It is 0.00496. So it's going to be replaced by the second limit. So positive. For the next iteration, we keep the first limit, and then we replace the second limit with the new midpoint, which is 1.9375. And then for the fifth iteration, our new midpoint is the average of these two, which is 1.93125. Let's look at the sign of fx at this new midpoint again, using our calculator. 1.93125. It is negative, minus 0.3, minus 0.0033. So getting back to our table, it is negative, meaning that for the next iteration we are gonna replace the first limit with this new point. So 1.93125. We keep the second limit. The midpoint of this sixth interval is 1.9434375. let's try the sign of fx at this new midpoint. 1.934375. It's positive. It's positive. And for the next iteration, for the 7th iteration, is going to be used for the first limit for AI. But as you can see here, we are approaching to the root because our number, are getting closer and it's converging to the root. So for example, with just using 2 decimal points, 2 decimal figures, we can say that our root is 1.93 with 2 decimal points. And yeah, that's the bisection method. And with this table, with this example, and with this graphing, we just showed how to use the bisection method, which is based on the intermediate value theorem. And I hope that this example actually is a very good one for you to understand the method. If you have any questions, please leave a comment down below this video and I will get back to you as soon as I can. If this video helped you in any way, please hit the like button and subscribe if you enjoy our content and would like to see more. Thank you.